Assalamualaikum and hi everyone. Did you guys ever wonder how you get from typing a website address to actually seeing it on your screen? So, in this video, our group will present a deeper explanation about the essential part of the internet, which is the DNS or the Domain Name System.
DNS or the Domain Name System is like the Internet Address Book, translating human-friendly names like www.google.com into computer-friendly IP addresses like 142.250.72.36. Imagine trying to remember a long string of numbers for every website you visit. DNS saves you the hassle, allowing you to type easy-to-remember names and instantly connecting you to the right site. Behind the scene, DNS server works fast, performing lookup to direct your browser to the exact online location you're searching for. This clever system keeps the internet user-friendly and efficient, making web browsing as smooth as flipping through your favorite playlist.
What is the difference between recursive and iterative? Recursive query have no delegation, which the initial server does all the work, while iterative query involve delegation, which the initial server refers the client to other servers to continue the lookup. We already know the definition, so now let me walk through how each of these processes works in more detail. The key steps in a recursive DNS query are: first, the client's device sends the initial query to the DNS root servers. Second, the root servers redirect the query to the appropriate area resolver, which is likely operated by the client's Internet Service Provider ISP or Service Provider SP. Third one is the area resolver then retrieves the requested information, which is the IP address for the domain www.example.com, and sends the final answer back to the client's device. In an iterative DNS query, the process works a bit different. First, the client's device PC sends the initial DNS query to the root server. Second, instead of performing the full lookup, the root servers refer the client to the appropriate .com.tld top-level domain servers. Third, the client's device then queries the .com.tld servers directly. Fourth, the .com.tld servers then refer the client to the specific DNS resolver for the domain example.com. Finally, the client's device queries the domain's DNS resolver directly and receives the final answer.
Hi, I will explain the DNS resolution process, which is how a domain name like www.google.com is translated into an IP address. Let's walk through each step. Step 1. Client device requests IP address. The client device, like your computer or phone, wants to connect to www.google.com. It asks the DNS resolver, what's the IP address for this site? So the step 2, DNS resolver checks cache. The DNS resolver checks its cache for the IP address. If it's not there, it sends a request to the root DNS server to continue the search. Step 3, root DNS server directs to TLD DNS server. The root DNS server knows it is a .com domain and tell the DNS resolver to ask the .com.tld DNS server for help. Okay, let's continue to the step 4. TLD DNS server points to authoritative DNS server. The .com.tld server doesn't know the IP either, but directs the resolver to the authoritative DNS server for google.com, which does. Step 5. Authoritative DNS server provides IP address. The authoritative DNS server for google.com has the IP address, let's say 142.250.190.78, and it sends it back to the DNS resolver. Last step 6. DNS resolver cache and respond to the client device. The DNS resolver saves the IP in its cache and sends it back to the client device, completing the request. So that's all for the DNS resolution process.
Implications of DNS server failures or attacks. First, service disruption. DNS server failures can make websites, email services, and other internet resources inaccessible. For example, a DNS attack could render critical websites unavailable to users. potentially causing economic loss and affecting business operations. Second, data integrity risk. Attacks on DNS servers can result in DNS spoofing or cache poisoning, where attackers manipulate DNS responses to redirect users to malicious sites. This can lead to data theft, phishing attacks, and compromise of sensitive information. Third, reduced network performance. DNS failures or overloads, such as through distributed denial of service attacks, can slow down the network, affecting user experience and productivity. Measures in place to prevent DNS issues. First, redundant DNS servers. DNS is highly distributed with multiple levels of redundancy, such as root servers, TLD servers, and individual domain servers. Most DNS providers operate multiple servers across different geographic locations to prevent a single point of failure. Next, anycase routing. This technique enables multiple servers in different locations to share the same IP address. Users are automatically routed to the closest or best performing server, which enhances reliability and resilience against attacks. Besides, DNS security extensions. DNS security extensions adds cryptographic validation to DNS queries, ensuring that responses are authentic and haven't been tampered with, reducing the risk of DNS spoofing and cache poisoning. Moreover, rate limiting and load balancing. Many DNS providers implement rate limiting to prevent DDoS attacks from overwhelming servers. Load balancing spreads the traffic load across multiple servers, enhancing response times and minimizing the risk of server overload. Furthermore, monitoring and real-time threat detection. DNS providers employ continuous monitoring and threat detection to identify unusual traffic patterns indicative of an attack. They use this data to quickly deploy countermeasures. Lastly, cloud-based DNS services. Many organizations now rely on cloud-based DNS providers, which leverage globally distributed networks, large bandwidth, and specialized security resources to withstand large-scale attacks.
Okay, that's all from us. Thank you for watching.